Greetings everyone. Tonight we're going to be doing sample problem 2.7 in Kinematics and Dynamics of Machinery by Charles Wilson and Peter Sadler. The problem itself is a problem about finding the location of links in a 4-bar linkage. This is the problem statement. I'll read through it very quickly. You can probably read it on the screen, but it may be a little blurry. Sorry about that. This is position analysis using the dot product method. And in it, a 4-bar linkage has the following link lengths. R sub 0 is 30, R sub 1 is 10 millimeters, R sub 2 is 35, and R sub 3 is 20. And we're to find the position of links 2 and 3 when theta sub 1 is equal to 45 degrees. This is what the setup of that problem looks like. You can see the figure here. In it we have R sub 0, R sub 1, R sub 2, R sub 3. I've noted the initial conditions here, along with the angle of R sub 1 to horizontal. I've also sketched in a couple of other things that we should make note of. This is theta sub 1, as mentioned. I've put in a dashed line representing R sub d, the diagonal of this linkage. I've noted our y and x coordinate system with the origin at this point. We also have several other angles mentioned here. Theta sub 2, which is the angle that R sub 2 makes with the horizontal. Theta sub 3, which is the angle going around that R sub 3 makes with the horizontal. And finally, phi sub b, which is the angle of the diagonal carried out beyond, between the diagonal and R sub 2. And as mentioned, we're to find the positions of links 2 and 3. Now, at first blush this looks fairly difficult, somewhat complex, but the first thing to remember, rule 1, is don't panic. Rule number 2, then, is to start with something that's fairly easy. And hold on a second, I think I'm going to change this so that we can just get a fixed focal length. Okay, hopefully that'll help. It's been going in and out. So rule number 2 is start easy. What can we do about this problem, or in this problem, that's very simple, just to get ourselves rolling? Well, this problem relies upon using vectors to solve for the positions of all the linkages. So, sketching in here, I'm going to have a vector R sub 0. My origin is defined here, so I'm going to set R sub 0 as a negative vector in the x-axis. Following around then for my closed vector chain, I can place my arrowheads on all of these vectors so that when I start at a location and follow around, I get back to the same location. That lets me state that R sub 0 plus R sub 1 plus R sub 2 plus R sub 3 is equal to 0. I also have this diagonal. I'm going to put an arrowhead on it. So that allows me to state some other things. For instance, I can say that R sub 0 plus R sub 1 is equal to R sub d. or rearranging it, r sub d is equal to r sub 0 plus r sub 1. Because I've defined this as my origin point, I can immediately write down a decomposition of r sub 0. It's 30 millimeters long. Its decomposition would then indicate that r sub 0 is equal to negative 30i. I also have a nice angle here, so I can figure out r sub 1 just by right angle trigonometry. And you can convince yourself that it is 7.07i plus 7.07j. Now this gets kind of fun. I have this lovely equation equating my diagonal with these two. So this becomes easy. I can simply add r sub 0 and r sub 1 and get r sub d. Let's do that. R sub d is equal to, I add my I components together. So let me grab my calculator here and you can follow along in the comfort of your very own home. And it's probably not going to show up very well, but we'll try it anyways. So I have a negative 30. I'm going to add 7.07 to it. So the first component for r sub d is negative 22.3i plus, and here I'm looking at j exists for r sub 1, doesn't for r sub 0, so it's just the same thing as r sub 1. Now a very important step is to make sure that these vectors match our sketch. We already know that r sub 0 is a negative I. R sub 1 should be positive I and j, and it is. R sub d is going from the origin back to the terminal point of r sub 1. So it should have a strong negative I component and a positive j component, which it does. So far, what we've done makes perfect sense related back to the sketch. Now we start to get into the fun part. At this point, we've got a couple of things that we can try and figure out. Let's see here. The first thing to probably do is to remember the law of cosines. The law of cosines is an equation that would indicate, for instance, that r sub d squared is equal to r sub 0 squared plus r sub 1 squared plus 2 r sub 0, r sub 1 cosine of the angle between them. Now, this gets kind of interesting because when we're talking about the angle between two vectors, we're not necessarily talking about this angle, because this angle reflects the supplement of the angle between these two vectors. The reason for that is that to get the angle between vectors, I need to have them tail to tail. Here I've got it nose to tail. So the angle that's being referred to is actually this one, which I'll call phi sub a. Now, if you're all following along at home, this kind of becomes a fairly easy plug and chug exercise. Let's go ahead and plug and chug them in. This is equal to r sub 0 squared, so 30 squared plus r sub 1 squared is 10 plus 2 times 30 times 10 times the cosine of phi sub a, which is just 180 degrees minus 45 degrees. So, plugging and chugging this in, I get 30 and I want to square that. 10 squared 2 30 times 10 times and the cosine of 135. So if I solve, that gives me that r sub d squared is 575.74. And therefore, r sub d is equal to 23.99, or we'll go ahead and use 24. So fairly simply, we've been able to determine what goes on here with r sub d. Now we can take advantage of the fact that we know r sub d. Remember that these are all vectors. So with this full definition of r sub d, right here, and a magnitude here, we can use the fact that r sub d plus r sub 2 plus r sub 3 is equal to 0. That should be evident from these vectors that we've drawn. So, r sub d plus r sub 2 plus r sub 3 equal to 0. Solving that for one of my unknowns, I can say that r sub 3, negative r sub 3 that is equal to r sub d plus r sub 2. Alright, now comes the magic, and this is what makes the dot product method, I believe, considerably easier than the vector analysis that we did in class last week using the cross product. What we're going to do is take the dot product of each side with itself. So I'm going to take this equation and I'm going to take the dot product of r sub 3 with itself, and that's going to be equal to the dot product of r sub d plus r sub 2 with itself. Now, if you look at the definition for the dot product, and I'll stick that perhaps in the margin right here, the dot product of two vectors, a dot b, is equal to the magnitude of a times the magnitude of b times the cosine of the angle between them. As we know, the cosine of 0 is 1. So if I take the dot product of a vector with itself, that very easily simplifies out to the magnitude squared. Kind of nice. Furthermore, if I go ahead and do my FOIL for these two products, I can simplify it out considerably. I'm going to have the dot product of RD, so that's just the magnitude of RD squared. The dot product of R2 times by R2, so R2 squared, and then 2 times the magnitude of RD, magnitude of R2, and the cosine of the angle between those two. Oops, R sub B, phi sub B, which is defined, as you recall, as this angle. And again, I extended this vector up so that I'd have the angle of these two when they're tail to tail. So this then, again, becomes a fairly easy plug and chug exercise. I know the magnitude of R sub 3, of R sub D, of R sub 2, and of course R sub D and R sub 2 here. And what I'm solving for is the angle between them. Once I have that angle between them, I will be able to use it, along with my sketch, to determine the orientation of R sub 2. So, manipulating that equation, what I find is that cosine of phi sub B, I'm solving for this, is equal to R sub 3 squared minus R sub D squared minus R sub 2 squared divided by 2 R sub D R sub 2. Solving for that. If you plug in your numbers, which I'm not going to do here just because we're running a little long, you will find that phi sub B is equal to 146.5 degrees. So again, looking at this picture, we just found out this angle. Now, there are a couple of other things that we should go through at this point, just from a geometry standpoint, so that we can figure out phi sub 2, and that will allow, or excuse me, theta sub 2, that will allow us to fully define R sub 2. So, one thing that we're going to want to get is the angle that R sub D makes with the horizontal. That's actually not too hard to get, because we do have the full definition for R sub D. So, right angle trigonometry lets us determine this angle as, let's see, well, we can do this a couple of ways because we do have both the full definition here and the length of the side. I'm going to go ahead and say that it's going to be, let's see, the height divided by the length here. So this angle is the inverse tangent of the height, 7.07, over the length, 22.3, which is equal to get 17. Does that make sense? Looks like it. Let me go ahead and double check though. 7.07. No, there we go. This is where it always becomes fun, doing it kind of semi-live. What I should get is theta 2. Okay, so there we go. Bear with me for a second. Okay. Okay. So sorry about that. I think that I misspoke here. Let's go ahead and use sine -1. And that's going to be 7.07 over 24, or 17.14 degrees. Therefore, if this is 17.14 degrees, then I should have that theta 2 is equal to 180 degrees minus 17.14 degrees minus 146.5 degrees and I get 16.4 degrees. Okay, so that looks good. Now, if theta 2 is 16.4 degrees and I have its length, all I need to do is decompose that into its I and j components. So drawing here, this length r sub 2 is 35. This angle is 16.4 degrees. Therefore, this side is 16.4, take the sine, multiply it by 35, 9.9. This side is 16.4 cosine, multiply it by 35, 33.6. Therefore, r sub 2 is equal to 33.6 I plus 9.9 j. And that again kind of makes sense given our sketch showing that r sub 2 is going to the right, so the positive x or I direction, and going up, so the positive y or j direction. Now finally, we can make use again of this equation. Negative r sub 3 is equal to r sub d plus r sub 2. We have r sub 2 here, just to remind us. R sub d is equal to negative 22.3 I plus 7.07 j. If I add those two together, I get 33.6 16.97j, but r sub d plus r sub 2 is equal to negative r sub 3. So this implies that r sub 3 is equal to negative 11.3i minus 16.97j. And again, that makes sense. Given our sketch, we should expect r sub 3 to be negative I because it's moving to the left, and negative j because it's moving down. So there you have it. This probably took a lot longer than I had hoped, but I was very verbose in stating it. And it hopefully should show you that the dot product method can be simpler than using the vector cross product method that we demonstrated in class on last Wednesday. This will be posted, and I will also take the sheet and scan it in and put it up, but hopefully you can all see it fairly well on the picture. And again, if you have any questions, please make sure to get them to me before class, which will be now tomorrow night. I'm posting this Sunday night, so that we can review them prior to your test on Wednesday. Good night.